Hello all, welcome to this video on linear algebra. Today we'll be looking into projection on general subspaces, Schmidt orthogonalization, and projection on affine subspaces. Assume that the basis vectors b1 etc. bm is an ordered basis of U. Any projection by u of x onto U is necessarily an element of U. Therefore, they can be represented as linear combinations of the basis vectors b1 etc. bm of U such that pi u of x can be given by sigma I is equal to 1 to m lambda I bi. As in the case of one dimension, we follow a three-step procedure to find the projection pi u of x and the projection matrix p pi. In the figure, we see the projection of the vector x onto a two-dimensional subspace U which has the basis b1 and b2. The projection pi u of x of the vector x on the three-dimensional space onto U can be expressed as a linear combination of basis vectors b1 and b2, and the displacement vector x minus pi u of x is orthogonal to both b1 and b2. The first step is to find the coordinates lambda 1 etc. lambda m of the projection with respect to the basis of U such that the linear combination pi u of x is equal to sigma I is equal to 1 to m lambda I bi, which can be written as capital B into lambda, where capital B consists of the vectors b1 etc. bm, and this makes B a matrix of dimension n cross m, and lambda consists of lambda 1 etc. lambda m, which belongs to the m-dimensional space, and this is closest to the vector x belonging to the n-dimensional space. The vector connecting pi u of x, which is an element of U, and the vector x must be orthogonal to all the basis vectors of U. Thus, we'll obtain m simultaneous conditions where we are assuming the dot product as the inner product as given here. The inner product of b1 comma x minus pi u of x is equal to b1 transpose into x minus pi u of x, which is equal to 0, etc. up to bm comma x minus pi u of x, which gives the inner product as bm transpose into x minus pi u of x, which is equal to 0, which with pi u of x as capital B into lambda, which we saw in one of the previous slides, we can write it as b1 transpose x minus capital B into lambda is equal to 0, etc. bm transpose x minus b lambda is equal to 0, such that we'll obtain a homogeneous linear equation system where we take all the basis vectors from the m simultaneous equations b1 transpose etc. bm transpose multiplied by the common element in all these equations, which is x minus b lambda, which is equal to 0. Now this vector can be replaced by b transpose. So we rewrite the equation as b transpose into x minus b lambda equal to 0. Opening the brackets, we get b transpose b into lambda is equal to b transpose x. The last expression is called the normal equation. Since the vectors b1 etc. bm are a basis of U and are linearly independent, b transpose b, which is an m by m matrix, is regular and can be inverted. This allows us to solve for the coefficients or the coordinates, which is given by lambda is equal to b transpose b, the whole inverse b transpose x. Here the matrix b transpose b inverse b transpose is also called the pseudo inverse of B, which can be computed for non-square matrices B. It also requires that b transpose B is positive definite, which is the case if B is full rank. In practical applications like in linear regression, we often add a jitter term, that is sigma I, to B transpose B to guarantee increased stability and positive definiteness. Now this ridge can be rigorously derived by using Bayesian inference. Second step is to find the projection pi u of x, which is an element of u. We have already seen that pi u of x can be written as b lambda. Therefore, pi u of x is equal to, substituting for the value of lambda, we get b into b transpose b inverse b transpose x. Third step is to find the projection matrix p pi. From the previous equation, we can immediately see that the projection matrix that solves for p pi x is equal to pi u of x must be p pi equal to b into b transpose b inverse into b transpose. That is the coefficient of the term x. The solution for projecting onto a general subspace includes the one-dimensional case as a special case. That is, if the dimension is 1, then B transpose B becomes a scalar, and we can rewrite the projection matrix P pi as B transpose by B transpose B. Now we'll see a problem where we are given a subspace with a span of two vectors which belongs to the three-dimensional space, and the vector x is given. We are asked to find the coordinates lambda of x in terms of the subspace U, the projection point pi u of x, and the projection matrix p pi. First, we see that the generating set of U is a basis, and also it's linearly independent. Thus, we can write the basis vectors of U into a matrix B like this. Then we'll compute the matrix B transpose B and the vector B transpose X. On substituting, we get the following values. Now we'll solve for the normal equation, that is B transpose B lambda is equal to B transpose X. To find lambda, we know the values of B transpose B and B transpose X. On substituting and solving the equations, we get the value of lambda 1 as 5 and lambda 2 as minus 3. Combining them as vector, we get the value of lambda. Then we need to find the projection pi u of x on the subspace U, and this can be computed by the equation pi u of x is equal to b into lambda. On substituting, we'll get this vector. The corresponding projection error here is the norm of the difference vector between the original vector and its projection onto U. That is the norm value of x minus pi u of x. On subtracting and taking the norm, we get the value as root 6. Next, we need to find out the projection matrix, which is given by P pi is equal to B into B transpose B inverse B transpose. On substituting the values, we substitute for B and B transpose. We have B transpose B but not its inverse. So we'll find the inverse of that matrix. For that, we'll convert it into the augmented form where we write the matrix on the left hand side, and on the right hand side we have the corresponding identity matrix. And we'll perform elementary transformations on this. Second row will be rewritten as R2 minus R1, which gives us 0 here. Then we'll do R1 minus R2 and rewrite R1, making this value as 1. Then we'll add R2 to minus 2 times of R1, giving a 0 here. Then we'll rewrite R1 as minus R1 by 6 and R2 as R2 by 2. After these steps, we'll get the identity matrix on the left hand side and the inverse on the right hand side. Now substituting this inverse into the previous equation, we'll get the final answer P pi as this matrix. The projections allow us to look at situations where we have a linear system Ax equal to b without a solution. Now this means that B does not lie in the span of A, that is, vector B does not lie in the subspace spanned by the columns of A. Given that the linear equation cannot be solved exactly, we can find an approximate solution in this case. The idea is to find a vector in the subspace spanned by the columns of A that is closest to B. That is, we will compute the orthogonal projection of B onto the subspace spanned by the columns of A. This problem arises often in practice, and the solution is called the least squares solution, where we'll be assuming the dot product as the inner product of an overdetermined system. Overdetermined system refers to a system of equations where the number of equations is more than the number of unknowns. Using the reconstruction errors we saw in one of the previous slides is one of the approach to derive principal component analysis. We just looked at projections of vector x on the subspace U with basis vectors b1, etc., bk. If this basis is an orthonormal basis, and if the two conditions for this is satisfied, which we discussed in one of the previous videos, then the projection equation simplifies to pi u of x given by b transpose b into x. Since B transpose B can be written as the identity matrix, then lambda will become B transpose X. This means that we no longer have to compute the inverse using the equation we saw before, which will save us a lot of computation time. Now we'll look into Gram-Schmidt orthogonalization. Projections are at the core of Gram-Schmidt method that allows us to constructively transform any basis b1, etc., bn of an n-dimensional vector space V into orthogonal or orthonormal basis u1, etc., un of V. This basis always exists, and the span of b1, etc., bn will be equal to the span of u1, etc., un. The Gram-Schmidt orthogonalization method iteratively construct an orthogonal basis u1, etc., un from any basis b1, etc., bn of the vector space V as follows. u1 can be written as b1, hence uk can be written as bk minus the projection of span of u1, etc., uk minus 1 into bk, where the value of k varies from 2 to n. In this equation, the kth basis vector bk is projected onto the subspace that is spanned by the first k minus 1 constructed orthogonal vectors u1, etc., uk minus 1. This projection is then subtracted from bk, and which yields the vector uk that is orthogonal to the k minus 1 dimensional subspace spanned by u1, etc., uk minus 1. Repeating this procedure for all the n basis vectors b1, etc., bn will yield us an orthogonal basis u1, etc., un of vector space V. If we normalize uk, then we'll obtain the orthonormal basis where the norm of uk is 1 for values of k ranging from 1 to n. Now we'll see a question where we are given the basis b1 and b2 for a two-dimensional space. We are asked to find the orthogonal basis u1, u2 of R2, assuming that dot product is the same as inner product using the Gram-Schmidt method. So first we'll find out the values of u1 and u2, since we have only two basis vectors b1 and b2. The original non-orthogonal basis vectors b1 and b2 is shown in this figure. u1 can be written as b1, which is directly given in the question. u2 can be written as b2 minus the projection of span of u1 multiplied by b2. On substituting, we get B2 minus the projection of span of U1 can be written as U1 U1 transpose by norm of U1 square multiplied by B2. All these values are available directly in the question. On substituting, we will get this vector as the result. The procedure of constructing orthogonal bases is given in these diagrams. Here the first new basis vector U1, which is given by B1, and the projection of B2 onto the subspace spanned by U1 is given. Then we'll construct the second orthogonal basis U2, which will give us this final image where we have both the orthogonal basis vectors U1 and U2, which is given by B2 minus the projection of span of U1 multiplied by B2. So far we discussed how to project a vector onto a lower dimensional subspace U. Now we'll see a solution to projecting a vector onto an affine subspace. Consider the setting that is given in this diagram. So we know that an affine space is denoted using a support vector and a direction space. The affine space given here, which is L, can be written as x0 plus u, where b1 and b2 are the basis vectors of u. To determine the orthogonal projection pi L of x onto the affine space L, we transform the problem into a problem that we know how to solve, that is the projection onto a vector subspace. In order to get there, we'll subtract the support point x0 from x and from L, so that L minus x0 will be equal to u, and that is exactly the vector subspace U. We can now use the orthogonal projection onto a subspace we discussed before and obtain the projection for pi u of x minus x0. X minus x0. This projection can now be translated back to L by just adding the support point, that is x0, such that we obtain the orthogonal projection onto an affine subspace L as pi L of x given by x0 plus pi u of x minus x square, x0, where pi u is the orthogonal projection onto the subspace U, that is the direction space of L. It is also evident that the distance of vector x from the affine space L is identical to the distance of x minus x0, from U. So that can be written as distance of x comma L given by the norm value of x minus pi L of x. Now we substitute for pi L of x given by norm of x minus x0 plus pi u of x minus x0. Opening the brackets, we get the distance from x minus x0 comma pi u of x minus x0, which can be written as the distance from x minus x0 and the subspace U. The diagrams here show the process. This diagram will reduce the problem to the projection pi u of x minus x0 onto the vector subspace U. Then we'll add back the support point, that is x0 to get the affine projection pi L of x. That's all for now. Thank you for watching.